Hello, my name is Miranda Howe and this is lab number 3, black hole. This lab has two parts. For part 1, the system is the star and the surrounding is the black hole and space. The purpose of part 1 is to find the mass of the black hole. And for part 2, the system is the spaceship and the surrounding is the star, black hole, and space. The purpose of the second part of the lab is to determine the initial velocity needed for a spaceship to fly close to the black hole. Two physical principles were used in this lab. The first one being Newton's second law. It states that the net force on an object is the changing momentum over the changing time. And the second one being gravitational force, which states that the force of attraction between any two bodies is directly proportional to the product of their masses and is inversely proportional to the square of the distance between them. And the formulas are on the slides. Here's the code for part 1. I used iteration to calculate the mass of the black hole, and this is the computational model that derived from this program. I would like to highlight this part of my code. As you can see, net force is equivalent to the derivative of momentum over the derivative over time. This is my code for part 2. Here I use the gravitational force formula F equals negative G times m1 m2 over r squared, as well as the position and velocity update formula V final equals V initial plus F net over mass times delta T, and R final equals V final times delta T plus R initial. I would like to draw your attention to this part of my code. In this while loop, I utilized the gravitational force formula and the position and velocity update formula to calculate the initial velocity of the spaceship. To answer the what does it mean question, the force parallel as previously stated is only the speed and not direction, so therefore, even if an object is accelerating, since the object is changing direction, there could be a net force still applied. If we look at linear moment, it would look like net force is 0, since all the forces would cancel as the displacement of an object would be 0. This is why we break the force apart into perpendicular and parallel components. And according to Newton's second law, F net equals dp dt, we can conclude that F net perpendicular is equivalent to the tangent of momentum over time, and F net parallel is equivalent to the direction of instantaneous velocity of momentum over time. Here is the graph of what it would look like if I wanted to enter into an orbit around the black hole. My velocities for both were relatively similar to make this pattern. To conclude this lab, I would first like to point out one possible source of error, which is rounding in iteration. When running the computational models, a lot of numbers were rounded, and after a few loops, there could be an inaccuracy of the result towards the end. And I also took a screenshot after each part of the lab. According to the first screenshot, the mass of the black hole is 1.06 times 10 to the 31st power kilogram, and according to the second screenshot, the planet's orbital speed would be 9.23 times 10 to the 6th power meters per second, and when it's put in vectors form, it would be negative 4.8 times 10 to the 7th meters per second for x component, and then for y component, it'd be 2.5 times 10 to the 6th power meters per second, and then for z component, it'd just be 0 meters per second.